decision ever made, but also like more than that, if you can find someone that does if you go to class, it's not bad. If you go to class, it's easy. I had the exact same show of Algorithms not bad.
All right, let's go and get started.
That one, I want like 50%.
Yeah. All right. So, today is going to be a mix of stuff. We're going to spend a decent amount of time going over the homework because there were somewhere around 3 different ways that you could have solved it, and I'm kind of curious who did what, and just to make sure that everybody knows about what other options there were, because some of them might be more relevant for like other CTF ponables. First, though, news trivia. So, no class next week because of Thanksgiving break. The homework that's going out tonight will just be due at the start of next class, so 6 p.m. Wednesday after Thanksgiving. I forget who it was emailed us about the CTF write-up not being included in the midterm grade, and the reason for that is basically we can't just make it like you did it or it doesn't count at all. It's either it has to be like a pass-fail for that too, and that would have pulled the majority of people's grades down. So we didn't include that, and it's not technically due until the end of the semester, right? So that's why it's not there. The main thing is just that as long as you see it as solved on like the challenge board, that's if you see that solved, we know it, and it'll be part of the final grade. Last note: so we have RC3 is this weekend. If you have not already do the write-up, we'll say it again. HXP is also this weekend. It is a more difficult CTF that the lab is going to be playing in. Feel free to play in either or both, of course. RC3 starts noon on Friday, yes, and runs 2 full. That's a really okay. Sure, why not? Apparently runs from just after noon on Friday until midnight Sunday night into Monday. HXP runs 48 hours. It starts at 7 a.m. on Friday and goes until 7 a.m. Sunday. Like I said, feel free to play in either or both. Lab will be playing in HXP. This is definitely easier, though, if you just need to knock this out quickly.
I would classify last year's RC3 ponables as easier than our homework problems so far.
So yeah, it's quite possible that the thing that you do a write-up on will be easier than this past homework. So this loads up again. So
basically what I'm saying is I expect to see a full list of everyone having the write-up done after this. Really good chance to knock it out, and I think the rest of the CTS for the rest of the semester are either extremely challenging or bad.
There's one more SecCon is in mid-December, but that's about it.
Challenging.
Yes. Dumb last time. That is still very dumb. Why is that? Okay, is that still readable to people? Like, it's dark, but is that readable? Okay. So briefly talking about the actual, overall ideas that were common pain points for homework. A lot of people got tripped up on, I realize this should actually be read, but if you called sendLine when you were writing the data that gave you RSP control, this is something that you just need to be careful about in general, right? fgets and read up to the given number of bytes, or basically to the first new line, whichever comes first. So if you send line hex 30As, that's actually going to be sending hex 31 bytes, right? So this new line is effectively going to just be stuck in the standard in buffer. So if you go to then ROP to read or something, read's going to effectively immediately return because it sees the new line, thinks it's done, and continues. This is something that, you do this once, and you should now be able to quickly-ish identify what's going on if that happens in the future. I guess the main takeaway, the easiest way to debug this is just, breakpoint after read is returned and look at REX, right? REX contains the number of bytes that gets or whatever read in, and if that's 1, well, there's probably an issue there. Another thing, there still seems to be a little bit of confusion, or we'll actually get to that one in a second. So Another issue was people who were trying to pivot to the very beginning of the name buffer. Again, what a lot of people saw would be either they would get garbage out when they were trying to read a GOT entry, or they would get a seg fault somewhere around like hex 600FD something. And of course, that is because when the stack continues to grow down, when you call gets, which calls something else internally, or when you call puts, which calls something else internally, which does those all need stack space. And those are just going to keep growing down, 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 until they get past the GOT and start hitting the dynamic section, which is read-only. So when they try and then write to their stack locals, you get a seg fault. Again, I don't really expect that to be an issue for most people in the future because the need to stack pivot, it's like itself is sort of rare in CTFs, to be honest. It's a very good thing to know because it allows you to do a lot of things and allows you to like continue ropping around if you run out of space or something like that. But yeah, so that was sort of a common issue. And then one last thing, this is what I was getting at earlier. There's still a little bit of confusion, it seems, with what the difference is between like the PLT entry for a function and the GOT entry for a function. And just to kind of cover that one more time, the GOT entries are just addresses, right? They are where you can find this function. So they're pre-populated when the program starts to point to the PLT entries, which are actual functions that set up a call to the dynamic link to the dynamic resolver to resolve them. After they've been resolved, they then point directly to the libc functions, right? So you call puts for the first time, it goes through the dynamic resolver, and then the GOT entry gets overwritten with IO puts in libc, wherever that's loaded into memory. Basically, the GOT entries aren't code, right? You can't jump to them. So those were the most common pain points. It seems like most everybody did pretty well. Took some people a few hours, but I think most people got through it in the end. So let's actually talk about like what techniques you could have used to solve this. So what I ended up doing is you actually set up, so you basically always start with call to puts to leak out a GOT entry, to leak out libc, right? Then, in my case, I opted to read back over a GOT entry with like the address of system or something that we resolved out. And then what's nice about this is that it's all one chain. There's basically no math involved about like if we want to reread in a second ROP chain with one of these two, where is it in memory? It's literally just you overwrite the GOT entry. You pop RDI with binsh, and then you just jump to the GOT entry that or you jump to puts, or I think I overrode libc start main. And so you just then jump to libc start main, that then jumps to the address that you overrode in the GOT, and you're all set up. I would say the second most common way to solve this was or maybe third most, I don't know exactly. Actually, really quickly, so show of hands. How many people solved it by overwriting the GOT entry and then just jumping to that? So 1, 2, 3. Okay, a few. How many people wrote a second, like in the call to read, they read in a second ROP chain immediately after their first, so you only had to do one pivot. 1, 2, 3, 4. Okay. And then lastly, how many people just read in the second ROP chain somewhere else in the name buffer and then pivoted again to that one? Okay, so it's actually almost perfectly distributed. So I guess they were all equally common. So the main thing though is I just want to walk through each of these because each one of these does stuff slightly differently. They may be easier for some people, right? If the one that you ended up doing was either like counterintuitive or you just couldn't quite figure out why something was not working, maybe one of the other ones will like make it a little bit more obvious, and they may be something that you can more effectively use in the future easily. So let's run them. All right, so we've got Gimbal. This is going to be a GOT overwrite. .py. So set up a process of gimbal, and we'll also create our elf of it. Another nice thing that I saw a lot of people doing was like really effectively using symbols out of the binary, which is like a really nice thing to see. Just, you know, cuts down on all the magic constants that you have floating around. So good job all with that. So first thing involved was, you know, we need to send line our fake stack, and then we need to, as I noted earlier, just send, not send line, enough to fill up the stack, plus whatever address we want to pivot to. I elected to pivot into symbols name plus hex1f00, just right near the very end of the buffer, so that I knew there's basically no chance of it growing down and starting to overwrite the GOT or anything important. I know some people used hex 1000, that should work just fine too. So we'll hack that, make sure we have an interactive. All right, so what do we want our actual ROP chain to do? So the first thing, and again, this was common for basically everybody, was we need to grab the puts GOT entry, or puts, or literally any other function that is guaranteed to be resolved here will work. libc start main, I think actually at this point they should all be resolved. And I also need my gadgets, so let's go ahead and grab those. And we'll be able to use most of this in the other demos. So anyways, RSI R15 is there, and I believe those were the only two gadgets that I needed. So we are going to RDI, and then the puts GOT entry, and then I guess just to say it in case people hadn't seen it, you can do symbols of GOT dot something, and then this will give you the address of the GOT entry, so even less magic numbers to have floating around. These are going to be the numbers, you know, like hex 601020 or something, that then hold the actual libc pointer or the pointer into the PLT entry. So then we actually need to call puts itself. Then, so at this point, we've now, in theory, leaked out a libc address. So we need to set up a call to read back in to get knowledge of where system is, in this case, back into the program. And we are going to, I'm just going to directly overwrite libc start main, because I know that will never get in the way of me trying to read or puts or leak other information out. You know, it's never going to be called again naturally. So we'll do that. Then, or sorry, this should actually be 0. 0, right? So the read takes a file descriptor. So FD0 standard in, the buffer where we're pointing to, and then count. And for those who didn't get all the way through it, if you were having issues and you were trying to use fgets, for example, the reason fgets really can't work here is because with fgets, the last argument is a file stream. This is not the same as a file descriptor, as like an integer file descriptor. This has to point to a structure, and that means you need control over RDX. However, if we grep dx, we'll see there are absolutely no gadgets that do anything with RDX in this entire binary, or at least that ROP gadget finds. So that pretty quickly eliminates the option of using fgets. RP++ might have found something else, I don't know, regardless. So we're setting up our descriptor. Then we need to say for the second argument, right, it is the address that we're reading into. So we're going to overwrite the GOT entry, and then, oh boy, that is completely not visible. And then we also need to fill up this R15, so we'll just give that garbage to fill up with. And then we actually need to call read. So elf.symbols read. So now at this point, once this is read back in, libc start main will have its address overwritten. And so we just need to set up a pointer to binsh. So pop RDI. And then this is really the only place that you actually have to do any math. So what I'm going to do is just at the very end put my binsh string. It's sort of important that this is at the end because again when the stack is growing down, if we put it before, it's possible that that will actually get overwritten with stack locals. So we want this to be just at the very end, the stack will never grow up. So we'll just leave it there. We know that we'll need our actual call to libc start main, which is now overwritten with system. And so then this offset is basically just going to be the pointer to here. And so this is the, or do you have it? Right, so our pivot base plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 keywords. So it is going to be pivot plus 12 times 8, right? 8 bytes for a keyword. Did I miscount? 8, 9, 10, 11. Okay, that sounds right. We'll double check all this in a debugger. So at this point, that should be the actual chain that we need. And again, the thing that I like about this is that it's just one contiguous chain that you just write in one place. And so it's a little bit more obvious what's going on. Instead, with the other ones, you have to have like 2 separate chains, one of which needs to be up here. The other one needs to be down near the bottom when you're actually responding to the read. So it makes it it can make it a little bit harder to read exactly what's going on in your exploit. But down here, let's also receive line and receive line there. Yeah, okay, so after, this is another point that I think most people got through eventually, but I'll just try and spell it out in case anybody's not like 100% confident with it yet. This does get a little bit confusing because you have this ROP chain up here, but then you actually don't interact with it until way down near the bottom of your script. So it can get a little bit hard to keep track of, like if I have, for whatever reason, if I needed to do 2 reads in the ROP chain up top, it can get a little bit hard to figure out or like to mentally correlate what you're doing down here and where it corresponds to the actual ROP chain. Unfortunately, that's just like how it works, right? So we send our stack. We have to send all of that before. Oh, sorry. So we have to send all of that before we can even think about getting control of RSP. So we have to send all of our ROP chain. We have to overwrite RSP here. We go through the leave. We now have RSP control. And now when the last ret inside of vuln, I believe, runs, that's when we really like fully get control of everything. So we do have to like actually interact with our ROP chain down here, which, like I said, can get a little bit confusing, but whatever. So our libc leak is going to be whatever we've leaked out. So from up here on line 11, right, the call to puts. So this is receiving from that call to puts. Chop off the last new line character, and again, we always need to append things to make this 8 bytes.
You have 2 colons there. 1 colon.
Oh, whoops. Yeah, thank you. We have our leak now in theory. Let's just print that out, make sure that it looks reasonable. And we actually need to load libc. So elf of lib 64 Linux GNU libc 606. I think I typed that in right. Let's see. So then we're going to set our base address to be our leak minus our symbol that we have for puts. So libc base should now be set properly. And again, let me just print this out, make sure I'm not missing anything. And then we should just effectively be able to respond with just the address of system. That's all that this ROP chain should need, since it's just overwriting the GOT entry for libc start main. We don't need to send it any more of a ROP chain, we should just be able to send it that address. So we should be able to do send line p64 libc.symbols system. Okay, so if all went well,
I think there was an S on inputs.
ah, very good catch, yes. Did I do that anywhere else? No, that looks fine. All right. So let's see. Nope, messed it up.
Oh, you need another receive line before your.
Oh, right, because of the K things by. Yep. So this raises a good point, and I'll talk about this one a little bit more when we look at one of the other methods. I want to do it remotely as well, because it gets really, really important to be keeping track of exactly where you need to be receiving lines and sending lines, because if you aren't careful, what can happen is effectively different sends can get collapsed together if you don't receive in between them to wait for the server to respond. This is just part of exploitation that is the most annoying, and this is especially super critical if you're playing on a server that's like in Japan or something, where it's easily 100 millisecond, 150 millisecond round trip. Everything is slow, and if you're sending all of your data like at the very front, it's almost certainly not going to work. So we'll see exactly what's going on with this, like I said, when we look at one of the other exploit techniques in just a couple minutes. But yeah, very good catch with that. EOF error. All right, so did we get... No, this is dead. Okay, time to gdb.attach on it. And we immediately die at address 0. Amazing. So we can, I think I know what I did. Yes, I know. Right, so I actually forgot to pad my stack. That would help. Now, one other thing that was, I think most, well, if you solved it, you had to get through this, but I'm not sure that everybody's entirely sure of why. This is not quite enough padding. And if you leave just this much, things will get really weird, because the leave instruction is essentially doing a move RSP into RBP and then a pop RBP. So when we hit the leave in vuln, that moves the RBP that was popped up inside of doit into RSP. So RSP is now swapped to what we control, but the pop RBP hasn't happened yet. So this actually needs to be 1F8, so that that pop RBP doesn't pop out our first instruction that we're trying to run with the pop RDI. I think a lot of people just added 8 more characters and it worked. But that's more like the exact reason why. Let me open this up in Binary Ninja and just make sure everybody is comfortable with that. 20 classic. Okay, so we're in doit. This is where we overwrite, right? Where we have a buffer of size 20. We're reading 28, so that gives us control over this saved RBP. This leave. Sort of helps, not really. That leave, like I said, is doing effectively a move RSP, comma RBP, so moving BP into SP, and then ret is popping RIP. So at this point, when we are right here, our BP is the value that we overwrote, and RSP is still normal. We then hit this leave, which now moves the value we wrote into our SP, and then that effectively immediately takes effect, right? It's not something that like updates at the end of the instruction or anything, or I know some other people were asking if they needed to pivot again later with a pop RSP instruction. That takes effect immediately. So as soon as you pop RSP, if there are any other pops in a gadget chain or anything else, those are all now immediately relative to the new RSP. So this then goes to pop RBP, and we need to add a couple more A's here to make that work. All right, so this is close. You can see we did get all the way into system at the very least. However, something is wrong, but yeah, libc base is looking correct, so that's all good. But you can see I must have miscounted the number of keywords that we used. I vaguely remember this being 11 in the exploit that I wrote, so let's just try 11. No, that is... Oh, did I forget? Try 13. There we go. Yes, it was 13, right, and because of the +8, I would add the extra one. But yeah, so we now have our shell. Cool. Exactly. So, all right, so that's method 1 for solving this. Let's take a look at another. So this is going to be reading basically right on, or not right on top of, but right below the first ROP chain that we read in. So this effectively, what's nice about this is that this prevents you from having to do another stack pivot. It might save you a little bit of time, but yeah, so let's go through it again. Pivot's the same, we need the same gadgets. We don't need, like I said, the pop RSP gadget, so we'll leave that as is. That stays the same, we still need to leak out libc, except this time, instead of reading over a GOT entry, we're going to effectively read to here, wherever stack would be here. So, right, this is all being moved into the buffer in one contiguous blob, and somewhere in memory, like, you know, hex 6020 something something something, this value will be stored. And we're going to write just after that, so that when read goes to return, it pops, you know, it pops RIP, what the return instruction does, but that RIP is the thing we just wrote in with the read call. So we can get rid of this, and if I did it right, this is going to be pivot. So again, we can just count the P64s basically that we use. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 10 because of the extra one up here, the +8. So at this point, a really easy way to test this is if we're off, we should crash at hex deadbeef. You know, just like in a normal ROP chain, this is where the next instruction would be. If we do it right, however, that deadbeef should actually be overwritten by this call to read. So now really the only other difference is that instead of reading in, or sorry, instead of just send lining the address of system down here, we actually want to send line essentially the entire rest of the ROP chain. So we're going to send, let's actually just make a variable here to make it a little bit more obvious. So we need to pop RDI, and one nice thing here is that you don't need to do the arithmetic to find binsh. You can actually just use a binsh that we can find in system. So we can just search through libc for the string binsh, and this will give us a fully resolved and this will give us a complete address since we set libc base on this line. Elf dot PwnTools' elf class dot search will return the string at the correct offset, including any base address if you set one. And so then after that, we just need to send our system. There we go. our system command, or our system instruction. Okay, there we go. So this should be the only change that we need to make. Again, if we didn't count something right, we should crash at dead beef. Otherwise, when this read goes to return, it should basically see this pop RDI as the next thing to jump to. We just wrote it directly underneath where this dead beef is and where it expects the return instruction or the thing to return to be. So we'll pop RDI, find our bin_sh string, and then call system. So let's see if that one works. Cannot convert argument to integer. I believe I thought libc.search would give you back a pointer. Perhaps my understanding of libc search is wrong. Let's see. So let's just print out search bin_sh. Ah, right. I forgot about that. Libc search returns a Python generator, so we need to basically tell it to just grab the first thing out of the generator, which you can do with next. Forgot about that one. There we go. Okay, cool. So, shell another way. Does everybody see how that one works? Does anybody have any questions? Do you want me to like attach GTB and look in memory to show you how like the two ROP chains kind of like coalesced into one, or one seed? All right. Let me actually just relaunch with GTB. All right. So let's break on read. I think, yeah, let's try that. All right. So, sorry. All right. So at this call to read, nothing should be in memory yet. Or sorry, actually, no, it should be. There we go. Now it should be set. Let's just take a look in memory. So if we examine, let's just say 10 addresses at, if I remember correctly, it's 601.080 plus our offset. Yeah, there we go. So at this point, we have all of the first drop chain that we read in, right? We see this is going to be a pop RDI number, puts, pop RDI again, number, pop RSI, number, call read, and then our dead beef. Now, if we set a breakpoint on this pop RDI instruction, we should hit this next immediately after read returns. And now if we look at the same memory again, maybe I need to hit it one more time. One more time. And it crashed. What? Oh, I hit it one too many times. Whoops. That was probably not the best thing to breakpoint on because it gets hit so frequently. Okay. Damn it. Well, okay, so you saw how it was the first time. We'll just look at it again here now. And yes, because I killed it. Damn it. Yeah. Okay. Now, so we continue once, step again. So we've leaked libc. So at this point, yeah. So at this point we're still good. We just have our first part of the chain read in. If we continue one more time. There it goes. Okay. So you saw before, this was dead beef. And now we've read in our second ROP chain to be right at this address so that when read goes to return, this is now the next thing that it executes. And we're now in the second part of our ROP chain that we just added. Does that make sense to everybody? Cool. All right. And then one last method. So, come on, align. No. Okay, whatever. All right, so let's take this one And we're going to do this now, but with two completely separate ROP chains, and we're going to pivot again between the two. So this first part is going to stay almost exactly the same, except we're never going to continue this ROP chain. We're going to call read, and then when read returns, we're going to need to find our pop RSP gadget, which is here. And let me add that in. All right, so we're going to pop RSP, and then we're going to let's go ahead and just decide where we want the second one to land. I'm going to say we're going to just use pivot plus hex 80, and that's just, again, it's basically an arbitrary place inside of the buffer. Again, it can be more or less wherever. We could even put it like earlier on inside of the name buffer, but we'll just add hex 80 and it'll drop it down a little bit. The one other change is that, of course, we aren't now reading into pivot plus this offset. We're reading just straight up into pivot plus hex 80. Now, again, like I said earlier, even though we have 4 total registers that are popped in this one gadget, this is the only one that's going to matter for this chain. Because as soon as this happens, all of these other pops are going to be relative to our new RSP, the thing that we just popped here. So in this second ROP chain, we need to first actually pad out hex 18 bytes of garbage to fill our 13, 14, and 15 with. Then it basically stays the exact same. Let's see, is it actually any different at all? I don't think it is. So we're doing the same thing. We're just dropping in system, pointer to system. Sorry, do you have a hand up? Sorry, okay. Just dropping in a pointer to binsh, calling system, and sending all of that. And in theory, this should, let me delete that breakpoint. I did. Thank you very much. Okay, and there's a shell again. So if we look at this one in memory, we'll see, we got that plus. Okay, so if we look at this one in memory, we'll see something slightly different to what we saw before, right? At this point, so yeah, at this point we definitely should have everything read into the first one. So you can see our first chain goes as normal, and then instead of directly reading in stuff here, we now should have a new chain. Continue again. I believe, yeah, there it is. So this is now the second part. This is now the second chain that we've read in. So there's our padding, and then another pop RDI, pointer to system, et cetera, et cetera, et cetera. Let's actually, just so that everybody can see this happening, let me set a breakpoint on this pop RSP, and we'll step through it. Okay, there we go. So, all right, we are just about to pop RSP at this point. You'll notice SP right now is 602FD8, and this will get popped, which is pointing us to 603000. So we'll step, and now you'll see our stack, again, as we expect, that's changed. And then again, these pops are now going to take 1, 2, 3 things off the stack. We read, and we're just back in to our call to system as we were before. So that's 3 different ways, completely equally valid, to solve this challenge. Hopefully one of those may have seemed easier to somebody if you solved it another way and it just didn't feel natural or something like that. This might be, one of those might be a little bit easier for you to get your head around. Yeah, does anybody have any questions about the 3 different ways? Do we want to go back through any one of them, walk through it anymore? Anything? Cool, all right. Let's go back to slides for just a couple minutes. We'll spend basically the rest of class looking at demos for the heap. So, this is basically where exploitation can get really, really crazy. Heap exploitation has a tendency of starting, like, you've got these pretty easy things to wrap your head around, and then it just explodes into something crazy that, like, very few people actually understand. So we're going to try and stick sort of on the easier side of it, because real weird heap exploitation is not something, you know, it's just, we could spend the entire class, like the entire semester most likely, on how the heap works, and still not get everybody on with it. So we're going to start off with just some generic vulnerabilities and just things to keep in mind when you're looking through code and you see heap stuff. So first of all, what is the heap? For those who don't know, it's just another section in memory. It is ASLR enabled, so it will be moving around just like libc and the stack and everything, and it's read-write. It's dynamically allocated in C through malloc and free. In C++, you'll use new or something like that. And yeah, this is how you interact with it. Basically, all the CTF challenges are just going to be calling malloc and free directly if it's sort of an easier / normal heap challenge. And some potential issues that you'll notice here. Well, we control when we allocate and when we free. So, there's a couple different things that can happen here. If we don't free an allocation, well, we get a memory leak, right? We have all these allocations that don't have any pointers to them that are just sitting around taking up memory. This is not exploitable, of course, but it's just bad, right? This is how a simple program takes up gigs of memory on your computer, because it's like allocating in a loop and never freeing stuff. We have the issue of what happens if we free something twice, right? Malloc returns a pointer, and if we try and free that same pointer twice, what happens? This is what I would say possibly exploitable. It depends a lot on other things in the program, if you know certain bits of information, and this is double free and those kind of heap, that kind of heap exploitations where it can get kind of tricky, especially with modern libc. There are now a lot of protections in place to prevent people from doing this. It used to be, with certain allocators, very easy, because free can, depending on how it's implemented, give you a relatively easy write, what, where primitive. And that's a very nice primitive to have, right? But recently, by recently I mean basically since like 2008-ish onwards, it's been made a lot more difficult to really exploit. But what we're going to basically talk about today, in addition to just getting familiar with how the heap works and some of the things that it does, is what happens if we allocate something, free it, and then use it again, right? This is just a place in memory. Once the memory exists, the OS isn't really just going to take it away from us, right? When we free everything, even if we have no allocations currently active, if we've allocated 10 things, freed all of them, the heap is still going to exist in program space. So what happens if we use it? Because those pointers are still valid, they're still pointing to memory, but you can get bitten very easily with these by using a freed pointer. Let's go through some demos. So let's start off with just basic heap stuff. So again, like I said, malloc is how you ask the heap to give you some space to use, and it just takes one argument at least, which is just the size in bytes. How many bytes do you want? How many bytes do you want guaranteed to have? It gives you back a pointer, and so you can make that pointer whatever type. If you have a structure, it's very common to just allocate enough space for a structure and then typecast that to a struct pointer. And again, it's just memory. It's just another pointer, so we can just start copy into it, free it, and call it a day. And so if we run this, you'll see we've gotten an allocation at some random address. We've stored something into it, read it back out, and we freed it, and we're done. Nothing fancy. This is just how the heap works, and you'll notice again, like I said, ASLR, so every time we do this, the addresses are going to be different. This should be relatively straightforward to most people, right? If you've taken any C, C++ language, you should be sort of familiar with this. Not super complicated. So let's take a look at something that gets us a bit more towards exploitation. So one of the things that the heap does, and I actually meant to put this up here, so some features that are nice for us. Low overhead allocations are just a good thing, right? You'll notice that when we got our allocation for the last one, it wasn't actually page lined though. It was page plus hex 10. And this is because the allocator actually keeps some space at the beginning of the allocations for itself, basically for housekeeping, to know what's where. But it's relatively low overhead. A couple important things though is that if you've allocated two things and then you free both of them, you don't end up with like two free chunks of memory. They get coalesced into one large chunk. So if you have two allocations of like size hex 20, they'll get coalesced into one blob of hex 40 size. Notably, sort of on that line of thought, when you go to then allocate something else, so if you like allocate free allocate, it uses a best fit against previously freed allocations to basically try and find a place that's already set up and ready to go. So if I allocate something of size 10, free it, and then allocate something of size 10 or less, it will get the exact same address most of the time, basically all the time with this allocator, but not guaranteed by all allocators, as the first allocation. And then another thing to note is that memory is not zeroed out between allocate, free, allocate cycles. When the OS hands you back the first page of the heap, that's guaranteed to be zeroed. But if I allocate something, store data, free it, then reallocate something, that second allocation, if it gets the same address as the first one, will have the contents of the first one still in it. It won't be zeroed. So this is just kind of demoing a few of those things. So you can see we grab an allocation of size hex 20. We just print out where it is, store a string into it, show that this does get saved, free it, allocate a new thing of size 20, and then without actually putting anything in B directly, we print out the contents of B. And then notably here, I'm also using A after it's been freed. I'm modifying A plus 8. I use plus 8 for a reason. We'll get into that a little bit more next week. So I modify A plus 8 to be the string modified, and then I print out B. And print out B was freed. So we get an allocation for A. We write stuff into A, print it back out, free A. We get B. Again, it's the same address. However, B already has a string in it, right? Because it's the same memory. A and B are now pointing to the exact same places in memory, even though from a programmer's mind, well, I called allocate twice, they should be different, but they aren't. Then if we modify A plus 8, B now changes, because again, it's the same memory, right? A and B are both pointing to the exact same place, so if we modify A, we're going to modify B. And then we just free B and clean up. So hopefully now you can start to see a little bit more why this can be dangerous, right? If you are not careful, if the programmers aren't careful about where they keep allocation, but basically if they aren't careful about making note that an allocation has been freed, it's very easy to use the same data twice, and potentially, in certain circumstances, you can get type confusion, which is what we'll talk about in just a second, I believe in the third demo. Yeah. Were there any points? Yeah, so just to kind of formalize this on the slides, like I said, the programmer is responsible for keeping track of what's been freed. C has no real memory safety. You can just like dereference a number if you want. And if you forget to null out pointers, or just somehow otherwise to note that this is dead, you have a dangling pointer. And in this case, it's possible where if you then use that dangling pointer again, you can potentially write to the memory of another object underneath it and that object will just, it's just memory at the end of the day, but something will be changed out from underneath it, which is potentially dangerous. So let's look at what we have here. So we have a struct that I've called a thing. There's some padding here, which we'll get into in a little bit about when we start to really look at like what the heap is doing when you allocate and when you free. And then we actually keep a function pointer in this structure that says, at this address is going to be a function that you can call with, in this case, a const char star. And in this case, I'm saying, this is going to print whatever string. Let's say you wanted to be able to print whatever in some unique way based off of some other data. I don't know. It's all for the sake of a demo. So we're going to allocate some largish allocation, size hex 80, and just print that out, write stuff into A, and show that it was actually written to, free it, and then you'll notice, again, we don't null out A or denote somehow show that it was dead, right? This is again a very simplified demo of something that would be more in the real world spread out across a big code base where you might have like a global list of pointers to allocations, and if you forget to null one of those out, you might still think it's still active. So we free it, then we allocate enough room for a thing. We set up the structure, so we just say, hey, the puts function, that's just what we're going to call, like that's the function that we're going to run, and then we're going to just copy a string into the string part, into the char array part of the structure, and then we're going to call the function. In this case, it should just be puts with the string. Now, say somewhere else in our large hypothetical code base, there is a reuse of A. A has been freed, but if it's not noted as such, it's still viable to think that you could use it, right? There's no other indication why not. So let's just edit it, and in this case, you might already be able to see why I'm exactly writing it as the uint64, but if you don't, we'll see in a second. So this is just kind of analogous to say, let's assume something else somewhere is like editing the the char star A, right? It's a character array. You should just be able to like start copy into it, right? We're going to run bfunc again, and that should still be puts, right? We set it to puts up here, and so we'll run it again, and we should get the same thing out as we did here. We'll free B, and I'll be happy. However, it died. Right, we run bfunc, first time is fine. We then modify A, which in theory, again, should be completely different, but it's not. It's just the same memory as B. So when we overwrite A plus 8 to be deadbeef, you can see if we run this, step through it, well, now we have like IP control, deadbeef. So this is probably like the most standard starter heap CTF type challenge, where you'll have an array of structures and you'll have a function pointer in one of them, some like in the function to delete whatever structure type it is, won't clear out that allocation, but it will free it. And so then you can allocate another thing on top of it of a different type and just overwrite some other sensitive property of the original allocation and cause it, to do something bad. Really quickly, does anybody have any questions about how this is working or why this is happening or anything like that before we move on a little bit? Everybody see why, right? Yeah. Okay. That's fine. So, starting from the top again, we allocate A, which we're just saying, this is going to now just be a car star. It's just going to be a pointer to some characters. And we're going to make it a relatively large allocation because we want to write some text in here, more than just a word. So we just print out what our allocation was, just to make it a little bit nicer to see, and we just stir copy into it, right? This is what you would expect with a car star. No compiler warnings, so sure, looks good. And we see, yeah, this did get overridden correctly. We then free A. This is kind of the critical line. Because when we then go to allocate B, the size of a thing is going to be 8 bytes plus 8 bytes plus 32. So 48, which is less than hex 80. So the allocator is going to be like, hey, when you go to allocate B, hey, I get this great allocation of size 80 that was just freed, let me just give that back to you, right? Assuming that the programmer was smart and noted that, okay, A has officially been freed and it's not safe to use anymore. But we didn't. So B and A now both point to the exact same memory. And so we initialize B, just set up, we say the function that you should use is puts, and here's a string, and we'll run bfunc, and all will be well. But then let's say you go along and you edit A, right? It's completely reasonable. And let's actually make this a little bit more. Let's just say we stir copy back into A, just a message of hello world. That should be long enough. Seems reasonable. Then when we run bfunc again, this dies. Because A and B point to the same memory. A, everything thinks is a character pointer, but B is a thing. And we actually can get rid of that, actually. So what we all think of as the first 8 bytes of A, right? We think of that just as 8 characters, just 8 bytes. If you look at that with the mindset of this thing structure, that's actually a function pointer. So when this is called, this is, you're going to effectively jump to that address. So let me build all this again. Okay, sure. Demo 3. So we allocate A. That's a fun allocation. Write stuff to it, free it. B, again, gets the same allocation. bfunc works. We're going to, this actually just realized because I changed it, this is now just writing over A. We run bfunc again, which is now going to be whatever we overwrote A with. Let me drop into the debugger so we can all see this. And so, let's see, we're now attempting to call RAX. RAX is the string hello world, or the first 8 bytes of it at least. So we're now attempting to call this function. Now, of course, this gets a lot more dangerous, where, let's say, system appears somewhere else in the binary. So we can modify this example pretty easily. We'll do the classic bin date here. And let's, what else do we need? Let's also, let's just stir copy. Actually, we'll just read from 0 into A of size. Actually, we'll read a little bit more. Let's read 32. So we can now exploit this binary, right? So let's do that for the sake of going through it really quickly. It's called Demo 3, I believe. So just realized we're going to need to send a lot of lines to get through stuff. Somewhere in here, we will be able to send system And then that's almost it. I believe the one other thing is I need to make the string that B takes in. This also needs to be a read. So string, and let's read that. Alright, so let me also just go through and count how many times I need to hit enter. 2, 3, 4. So, okay, so 1, 2, so the third one. Oops. Okay, so this third one in theory should be the string that gets echoed out. So let's just say we really want to see the string bin_sh. I believe then we have another 1, 2, 3. Looks like I needed one more. Right, I'm gonna modify. And then in here, this is where we can send, the thing that we want to overwrite. Looks good. Let's also just run this under a debugger, make sure I didn't attach P. Alright, Python demo 3. Okay. And oh, nope. Let's see. So we got Sigil, RIP. That's interesting. Oh, I see what's happening. Okay. So let's really quickly just make sure I'm doing this right. So 1, 2, 3. Send bin_sh. No, that must have been wrong. What am I doing wrong here? That should be fine. And then print that out. Am I off when I one of those there? Okay, one of those two. We'll just spam it. Why not? And then in here, we'll actually just dump that too. Demo 3. Why is that not hitting enter more times? Come on. Why would that be happening, actually? Doesn't make sense. Is it possible? Oh, do I need to, like, disable? Oh, yeah. Let's try that. Okay, that looks better. Yeah. So we've now made our program exploitable. That was relatively easy. You know, and that's all. It looks like I messed that up. Whatever. We saw we were able to jump into system, right? That's really what matters at the end of the day. And that's all just due to the fact that this one line was called. If that line is removed, this is not exploitable anymore. So yeah, does everybody see how that one works? Where since A and B are just the same pointer at the end of the day, we can overwrite B's function pointer kind of underneath it because, oh yeah, we're modifying A, but we aren't. So, well, we are, we're also just modifying B's at the same time. So does everybody see how that works? Cool, okay. Let's take a break since it's past 7. We'll come back, do a little bit more demos of just, watching the heap in action, watching it, coalesce stuff, seeing what all that padding is at the beginning, and kind of go from there. So let's be back at, like, say, 7:25-ish, 15 minutes, so.